In this video, we're going to be talking about the definition of a rational inequality and then also how to solve a rational inequality graphically. Now, a rational inequality is when we have f of x equaling a rational expression, and then we set that less than to 0 or less than or equal to 0, greater than 0 or greater than or equal to 0. And as a quick refresher, remember that a rational expression would be when we have like a p of x divided by a q of x. Now there's one difference in solving a rational inequality and a polynomial inequality. And that's that a rational inequality, such as f of x is less than 0, let's say, the list of boundary points must include the real solutions to the related equation of f of x equals 0, along with the values of x that make f of x undefined. Let's take a look at a graph. Here we're looking at the graph f of x equals 2x minus 5 divided by x plus 2. Notice that the function changes sign to the left and the right of the vertical asymptote x equals negative 2, and to the left and to the right of the x-intercept 5 over 2 comma 0. Now something to note here that can be a pretty common mistake is that the graph of a rational function will not always change sign to the left and the right of a vertical asymptote or the x-intercept. However, since the possibility exists, we have to test each interval defined by the values of x. And so that's what we're going to do here. So we're going to use our graph. We're going to move it down with us as we go. But we are going to, we might not need to, there we go. So we want to know when our f of x is less than 0. So where are we in the negative? And we see that that's going to be happening from negative 2, from here all the way to our 5 halves. So we can go ahead and write that down. So it's going to be on the interval from negative 2 all the way to 5 halves. And then the next question says, where are we greater than 0? And we can see that that happens from here all the way up to our y equals negative 2. And then it happens from our 5 halves to infinity. From our 5 halves to infinity. So we would write that as negative infinity to negative 2 unioned with 5 halves to infinity. So where exactly are we less than or equal to 0? Now in this particular instance, we are less than or equal to 0 here, and we get to include our x-intercept because that's where we equal 0. So we get to include that this time. So here we would say that we are less than or equal to 0 from negative 2 all the way to 5 halves. And this time we get to have a closed bracket because that 5 halves is included. Let me scoot this up just a little bit. There we go. So our 5 halves is included. So now where are we greater than or equal to 0? So we see that that happens from, again, negative infinity to negative 2. And then from this 5 halves all the way to infinity. And we get to include our 5 halves this time. So we would write that as negative infinity to negative 2, unioned with, and then close bracket, of 5 over 2, all the way to positive infinity. Now, a common mistake is people including that negative 2. But notice that we don't include it. We have a parenthesis there instead of a closed bracket. So the value negative 2 is excluded from the solution set because negative 2 makes the expression 2x minus 5 divided by x plus 2 undefined. So we cannot include that negative 2 in our solution.